Okay, welcome back everyone. So welcome back to another video, and in today's video we are basically just going to be doing another number theory exercise because these tend to be pretty fun. So this is a two-part question. The first part asks us to show that n times the expression n times 7n plus 1 times 2n plus 1 is divisible by 6 for all n. So we're going to be using modular arithmetic to solve this. And it's not technically necessary, but I think doing it this way is very elegant. It's pretty elegant. So let's get started. So notice that if if some expression is divisible by 6, in other words, 6 divides our expression in this case. So we're asking for whether 6 we're asking to show that 6 divides this expression for all n, right? So this also means that 2 divides all the that also means that all the divisors of 6 also divide this expression. So therefore 2 divides our expression plus 1 2n plus 1, and 3 divides our expression 7n plus 1 2n plus 1, and of course 1 divides our expression. And this is kind of trivial, so we don't have to write this since 1 divides any value or any expression. So these are the two key ideas, and we know, and I feel like, and working in mod 2 and 3 is much easier than working in mod 6. So why don't we get started with this? Okay. So first, well, let's just for okay, well, let me back up here and say that it suffices to show that this expression is divisible by 2 and it is also divisible by 3, since since 2 and 3 are coprimes, so the LCM of them is 6. So that's why that works. So let's do that. And the way we're going to do that is we're going to express express the expression in the given modulus. So if this is the case, we want to show that our expression here is congruent to 0 mod 2. In other words, it's divisible by 2, or it's always even. So in other words, our expression n 2n plus 1 times 7n plus 1 is congruent to some residue R1, which we want to show as 0. So 0, so mod 2. So that's what we have to show first. So we can actually simplify this a bit in this given modulus, and that's to say that, well, this here 2n is always divisible by 2. It's always a multiple of 2, in other words. So as a result, in modulo 2, it's just congruent to 0. So in other words, 2n is congruent to 0 mod 2, since these two things have the same remainder when divided by 2. So this just goes away, and this just becomes n, because we can separate this into 6 and plus n. 6n is divisible by 2, so therefore that just is congruent to 0 mod 2, and we're just left with n. So all in all, we just have, well, we're just left with a 1 here. So all in all, this is congruent to n, well, times 1, so times n plus 1, which is congruent to our R1 mod 2. And let's notice something here. Well, these are two consecutive integers, and I need to make it clear that n is some integer. So in other words, n is a member of the integers. So this is key. Okay, so I guess for n is a member of the integers. Okay, just need to make that clear. So these are two consecutive integers, right? And it's important to note that, well, one of these must be even, because if n, let's just say n is odd, so therefore, if n is odd, well, then n will be equal to, I'm just getting a bit too rigorous here, but because that's kind of self-explanatory, but then n will be if n is odd, then it's just gonna take the form 2 times some k sub 1 plus 1, and therefore n plus 1 would equal 2 times, uh, sorry, 2 times k sub 1 plus 1, and this is now a multiple of 2. This is divisible by 2, right? So that's that's why that works. And if n is even, well, then we'll just get that n is just some 2 times k sub 2, where k sub 1 and k sub 2 are just some integers. And if we add 1 to that, then that'll take the form of an odd number. So one of those has to be even, and therefore our r sub 1 is 0, right, for all n. So we've shown the first case. Let me just reload this tab. Okay. And I think I'm just going to duplicate this to go on to the second section. Just quickly. So let me get rid of all this work here. Okay, so our first part of the plan is done. So now let's show that our expression n times 7n plus 1 times 2n plus 1 is congruent to some r2 mod 3, where we want to show that our r2 is 0. So, and this again is just saying that this is always divisible by 3. So we can again break this down into, we can again simplify this in our given modulus. And that is to say that, well, this here is just 2 times n. Well, let's get with the more obvious part. So this is 6n plus n, as we said earlier. And 6n is always divisible by 3, since the prime factorization of 6 includes 3 and 3. So therefore, therefore 6n is congruent to 0 mod 3, and we're just left with n. So therefore 7n is congruent to n mod 3. And also 2n, well, that's just 2 times n, and, well, 2 is just congruent to minus 1 mod 3, right? Because it yields the same remainder when divided by 3. Because, well, let me just be more clear about that. If 2n is congruent to, well, let's just say this. So 2n is congruent to, well, this is our statement, is congruent to minus n mod 3. Okay, so that implies that, well, 2n equals some constant times 3 minus n. And therefore we just get, if we add this to both sides, we just get 3n equals 3k. And that holds, right? So that is why that works. And hopefully that makes sense, because if we just look at the constants, again, 2 is congruent to minus 1 mod 3. Okay, and I want that to make sense because, well, the thing is that, how should I word this? Well, 2, okay. Well, if 2 is congruent to, well, 2 is congruent to, 2 is congruent to 2 plus 3k mod 3, where k is some integer. It can be negative includes negative and non-negative integers. So if k is negative 1, then we just get negative 1 here. So this does hold. Okay, because we can express 2 in this congruence as being equal to, well, obviously 3k. In the congruence, 2 is congruent to 2 mod 3, that we can express this as 3k. 2 is congruent to 3k plus 2, right? So yeah, and as a result, this is trivial because if these two are equal, we can substitute 3k plus 2 for 2 here, and that's why that works. So for some reason I just got caught up on that simple thing there, just trying to explain that. So yeah, that's why that works. Okay, so now let's simplify this. So here again we get n, and this becomes, well, we want this to be, we can have this to be minus n. So we just get n times, so this is congruent to n times n plus 1 times minus n plus 1, which is congruent to, well, let's just factor that minus sign out there because this is kind of nice, and we have a very close form to 3 consecutive integers, right? So let's factor that minus sign out of there. So we just get minus n times n plus 1 times n minus 1. And notice, let's just put mod 3. And notice that these are 3, if we just focus on this, these are 3 consecutive integers. So therefore, and this minus sign won't affect any of our results, right? So we can kind of just ignore that for the time being. And notice that these are 3 consecutive integers, right? N plus 1, and n minus 1. So at least one of those must be a multiple of 3. And therefore, if one of those is a multiple of 3, the entire expression will be a multiple of 3, will always be a multiple of 3, and therefore we've just shown that this is always a multiple of 3. And therefore we've shown that this expression is always divisible by 2 and 3, and therefore it must also be divisible by the LCM of those two numbers, which is 6. Okay, so that's part A done. So on to part B. So let's go. So part B, when is this expression divisible by 12? So basically it's asking to find the values of n that allow for this expression to be divisible by 12. And let's see what two numbers, or yeah, what two divisors of 12 where the LCM of those two divisors is equal to 12. So notice that the LCM of 3 and 4 equals 12. And we've already shown that the expression is divisible by 3. So that's your check mark. But it suffices now to show that our expression is divisible by 4. So now we just have to show that 4 divides our expression. And 7n plus 1, 2n plus 1. And it's important to note that, well, we notice that this section is odd no matter what n we plug into there. So therefore, this won't affect whether this is divisible or not. Since this is always odd, and 4 and in any odd number, since 4 will not share any divisors with an odd number, with an odd integer, since the only divisors of 4 are 1, 2, and itself, which are all even, and they even numbers don't divide an odd number. And no even numbers divide an odd number, right? Okay. So in other words, we can just leave this off. Okay? So now it suffices to show that 4 divides n times 7n plus 1. Okay. So, well, we can look at this in a modular congruence. So we just have n times, well, if we simplify this, well, this is congruent to, I'll just speed this process up. This is congruent to minus n mod 4, so we just get minus n plus 1 So so basically n 7n plus 1 is congruent to n times n minus 1 plus 1 is congruent to minus n plus 1. And then mod 4. And something else that's pretty important to note is that, well, look at this. So these are two consecutive integers, right? And we know that two consecutive integers are always coprime. And that's because, well, the only possible factors they share is the only possible factor they share is 1, and therefore they are coprime. So, I mean, that's pretty trivial, but so these two integers will always be coprime, right? And therefore, if they're coprime, they don't contribute anything to each other when dividing 4 by by these two. So in other words, and again, we can kind of ignore the negative sign because that won't affect anything. It's kind of like taking the negative sign out of a fraction and just evaluating the fraction and leaving the negative sign till the end, right? So in other words, either 4 divides n or 4 divides n plus 1. Okay? And the only time that this works is, well, either, so if we want to express this as an equation, either n equals some multiple of 4, right? So we'll call this 4a, or well, these are our two cases, in other words. So, and basically, and so what we can't stray too far away of what we're doing here. Basically these values of n, if some integer n takes these forms, then this entire expression will be divisible by 12, right? So and n equals, well, basically we can write this as n plus 1 equals sum for b, well, sum for b, right? So therefore n equals 4b minus 1, or n equals 4b plus 3. So there we go. Okay. So that is basically our answer. And yeah, so oh wait, hold on. I think we've actually made a bit of a mistake here, because if we consider this, so 4 because this must be this, therefore this must be 0 mod 4. So n is congruent to, yeah, that should be correct, right? Okay, so this should be correct. And so hopefully you enjoyed this video, and have a nice day, and goodbye.